two people have energy. Hi, Victoria.
Hi.
Sorry, I'm getting my ears in. Hi, Victoria.
Hello.
People are streaming in little by little. How you doing tonight?
I'm doing okay.
All right, wonderful. Okay.
Hello.
Hello. Victoria's here. Oh, I hate this. You know, it drives me crazy because every time I'm looking here, I try and write down names, and then what happens is the names, they change on me. Who's Grazie? I'm sorry, I gotta let him in first. Who is Grazie? Guys, who is Grazie? Okay. How we doing? Everybody okay? All right. Kara's in. Maybe Kara's in. Victoria's in. Veronica is in. All I got to do is find out where her name is. There we go. Okay. Grazie. Grazie.
Me?
Yeah, that's you. Who are you?
Oh, I'm good. How are you?
I'm sorry, who are you?
Graziele Teodoro.
Ah, got you. Okay, thank you, Graziele. Okay, I got 12 people in. Aisa, not in yet. Devin, hasn't been in yet. I think I kicked him out. Madison, is Madison here?
She's here.
Was that Madison? Where are you at? I'm not seeing you on the list.
I'm here. I'm here.
Under what name?
Madison Fernandez.
Got you. Ramiro. Tin, I see you. Yes, you're there. Okay. Brittany. And hopefully other people come in. Okay, guys.
You didn't say my name.
I got you. Swear to God.
Perfect.
Very easy lab. How many of you remember densities from last semester? This lab is easier than even that one is. Okay? So we're going to get this, hopefully. I'm not going to promise we're going to be done by 8 o'clock, but we're going to give it our best shot. Okay? By the way, did anybody have trouble with the new time? Finest kind. Maybe one of the other people had problems. If so, well, I'll deal with it at that time. All right, so let's get this show on the road. We excited about densities? I know I'm very, very thrilled about it. All right, first thing. Have you guys been shown the density triangle at some time or another? Cassandra's shaking her head very strenuously. You're going to strain your neck, Cassandra. Are we good with this?
Yes.
All right, the density triangle. Basically, you put the mass over the density and the volume. And the line everything, tells everything. Okay? If you have the mass and the volume and you want the density, there's a line between the mass and the volume. Divide them. Divide the mass by the volume, you're going to get the density. On the other hand, if you have the mass and the density and you want the volume, again, there's a line between them. Divide them. Divide the mass by the density, you will get the volume. Now, if you have the density and the volume and you want the mass, you have to multiply them. Now, let's see what's happening. Let's see what's happening with these things. Mass is going to be in grams. Volume is going to be in milliliters, centimeters cubed, cubic centimeters. I mean, something like that, right? Now, if we look at density, density is always in mass per volume units. So you don't have to memorize the density triangle. You just got to look at this stuff. Density is going to be mass over volume. So if you have a mass in grams and a volume in milliliters, just divide the mass by the volume. You're going to get the right answer. Okay? If you have the volume in milliliters and the density in grams per milliliter. Look, if you take the volume and you multiply it by the density, milliliters are going to go away. And if we multiply them, we're going to be left with grams. Make sense? All right, now the difficult one. If we have mass in grams and density in grams per milliliter. Look at how we're trying to, look at where we're going to, guys. We want to end up with milliliters. If we have the grams and the density and we want to find the volume, we want to end up in milliliters. If we just multiply these straight, we get grams squared over milliliters, which does us no good. But if we multiply by the inverse, in other words, if we take the mass and we multiply it by the milliliters over the grams, or in other words, divide by the density, we're going to end up with the volume in milliliters. Fair enough, guys? I probably belabored the point too much. So, liquids, Cassandra. Cassandra.
What's
up? Do you have a bathroom scale?
No, I don't.
You don't? No scales at all?
My mom has one.
Okay, good. You can borrow it for a second, can't you? She'll let you, won't you? Won't she?
Yeah.
All right, so what I want you to do is I want you to go right now, go get the bathroom scale, put it down, and I want you to go to the sink. Open the faucet up, put your hands beneath the sink, and I want you to tell me how much a handful of water weighs.
A handful of water.
Go for it. Go now.
You want me to get like a cup?
No.
Okay.
Wait a second here. What an idea. What a concept, Cassandra. Look, she thought, oh, if I use my hands, it's going to all drip through, right? But if I use a container, I can get the weight of the container in the water. Now, Cassandra, if I have the weight of the container in the water, what other little bit of information do I need to get the weight of the water?
You need to put the water in the cup and you need the weight of the empty cup.
You need the weight of the empty cup. So you can't measure weights of liquids directly. You can't do it. You try and pour the liquid on the scale, it's going to go all over. It's probably going to go over the edges and create a big mess. Your mother's going to get upset at you for making her scale rusty. All right. So you don't want to do it that way. No, don't do it that way. What you do, you take the cup, put the cup on the scale, record the weight. Then you put the stuff in. Whatever liquid you want in the cup, put that back on the scale. Now, Veronica, you have the weight of the cup and the liquid, and you have the weight of the cup. How are you going to get the weight of the liquid?
Don't you subtract them?
All you got to do is subtract them. Remember, this is the weight of the cup and liquid. You have the weight of the cup. If you subtract them, the only thing that's left is the weight of the liquid.
Mm-hmm.
Now, Madison. Madison?
I'm here. Sorry, I'm here. I'm here.
You sure you're not asleep now?
No, I just couldn't find the unmute button.
All right. So, Madison, we just got done saying that you can't measure volume directly. Do you believe that? Oh, so you can't measure mass directly. Do you believe that?
Yes.
Okay. Can you measure the volume directly?
Yes.
How do you do it?
With a measuring cylinder?
Yeah. All you got to do, you get something that is marked with measurements, pour the liquid in there, and then all you have to do is read it directly. So liquids, you read the volume directly. The mass you have to do indirectly. Is this making sense, guys?
Yeah.
Okay, so we have just an example. The mass of the container without the liquid is 32.643. The mass with the liquid is 42.893. I subtract the two of them, I get 10.250. I read the volume directly. I divide the 10.250 by 10.2. I get 1.00 grams per milliliter. Do I have any questions on this? Okay. Now, we just talked about liquids. I got to see who else is in here. Alex, you out there, Alex?
Yes.
Okay, Alex. We just got done saying you can't weigh a liquid directly, but you can measure the volume directly. What about solids? Can you weigh them directly? Can you just take a solid, take it over, put it on the balance, and get the weight? Can you do that?
Yeah.
All right, pretty much, yeah. What about the volume? Can you measure the volume directly?
Not normally.
Not normally? I like your waffling, Alex. You're doing a very good waffle.
Okay.
You're wobbling here, Alex. What do you mean by not really, possibly never?
I mean, like with a cube, you could measure the sides, but if it's like a rock or something.
Very good. If it's regularly shaped, if your solid is regularly shaped, you can measure the parameters. And once you measure the parameters, you can plug that into a formula and get the volume. If we have the volume of a cube, all you got to do is measure the side and take that side measurement, multiply it by itself, and multiply it by itself again. We have the volume of the cube. If we have the volume of a block, measure the length, width, and height, we have the volume. Sphere. Genuinely speaking, guys, it's easier to measure the diameter of a sphere rather than the radius. So what you do is you measure the diameter of the sphere, half that, make it half. Then you use the formula 4/3 pi r cubed. That will get you the volume of the sphere. If you have a cylinder, measure the height, measure the diameter, take the diameter, make it in half, then the volume of that cylinder is height times pi times r squared. Regular shape, piece of cake, easy. All you got to do is make sure that you get the measurements right. Then you're going to have the volume. Then you can directly measure the mass. You got the density.
Professor,
Yep.
I have a question.
I have an answer.
Going back to like the bathroom scale analogy, I just wanted to ask, wouldn't that like be inaccurate because it's not it measures weight and not mass? I don't know. Would that work or no? Like in a lab? Because the scales in there, aren't they different than
No,
like a spring balance
they're
scale?
not different. The only difference is the fact that you're dealing with pounds with a bathroom scale as opposed to grams.
Okay.
It's the same difference.
Okay.
The only, okay.
There was a question in lecture about that, like a spring balance scale only measures weight, but it doesn't measure mass or something. I don't know.
Who do you have for lecture?
Miss Mitchell, Kathy Mitchell.
Okay, did she bring it up or did a student bring it up?
No, I'm online, so it was like an online question. So I just wanted to see if that was right.
I'll be honest with you, Cassandra. I don't know. That's something I'm going to have to look up. Okay? My thought is mass is mass.
Yeah.
And weight is weight.
Right.
Okay?
Yes.
Mass meaning if you take a object from the earth, take it over to the moon with less gravity, it's going to weigh less. Take it to Jupiter, it's going to weigh more.
Right.
But the mass doesn't change.
Exactly.
Okay?
Okay.
Does that answer your question? I will get back to you on that.
Okay. Thank you.
Okay, Cassandra? Spring scales, gravity.
Or like spring balance, something like that.
You know, some professors get these things in their head and it's like this overriding. It's like they were punished when they were a chem student. So what they end up doing is they're going to punish you. And they're going to say, okay, if there's a difference between spring balances and other balances, and spring balances give you weight, whereas other balances give you mass. And you better know the difference or else I'm going to slap your hand silly. Right, Cassandra?
Yeah.
All right. Rule. This is a life lesson. Deal with the professor. If the professor is insisting that a spring balance measures mass or measures weight and the other kind of balance measures mass, then go with the flow.
Okay.
Okay?
Okay. Thank you.
She's probably right, Cassandra.
Okay.
But she's probably right. But I'm telling you straight out, I don't give a damn.
Okay.
All right?
Yeah.
There are too many important things in this course that you have to get straight to be silly, sitting there sillily, and I'm an English major, to be worried silly over whether you're measuring mass or weight. Okay?
Okay. Thank
All
you.
right, a bar. A bar has a length of 7.80 centimeters, a width of 4.75 centimeters, and a height of 1.45 centimeters. Its mass is 354. I was real nice here to you guys. Do you notice all the numbers have 3 sig figs? We're dealing with densities. We're dealing with multiplications. We are going to end up with 3 sig figs. So I've got the volume, which is length times width times height. That volume, if I multiply those 3 numbers out, ends up being 53.7 cubic centimeters. I figured out this is not volume. This should be, yeah, that's volume. What am I talking about? The mass is 354. Okay, so in order to get the density, I'm going to take the mass and divide it by the volume we figured out by measuring. Now, if we have an irregular shape, guys, I got to tell you a story. Way back in time, there was this Greek king. He's an evil old guy, rotten, nasty person. What he liked to do is he liked to go over to the neighborhood kingdom and slap the snot out of some other king. Now, the other king kind of got tired of having the snot slapped out of him. So he decides to present the Greek king with this gorgeous golden crown. Now, not only was this guy nasty and mean, he was also skeptical. So he went over and around and found his favorite Greek geek called Archimedes. And he said, Archie, what I want you to do is I want you to prove whether this is pure gold or not. And oh, by the way, you're not allowed to mar this beautiful crown in any way. And oh, by the way, you got a week to do it. And oh, by the way, if you don't do it in that week, I'm going to kill you. Well, this naturally concerned Archie. So he fretted and paced. Then come around Tuesday, he paced and fretted. Went all around, half of his hair was getting pulled out. He didn't know what he was going to do. So finally, he decided to go into the place where he does his best thinking, the bathroom. And when he decided he was going to take a real nice, long, warm soak in the tub, filled it all the way to the brim, and he got his little tushy in there. And he started noticing as he put his tush in, water came out. And as he put more of his body in there, more water came out. So he said, Eureka, I know what I'm going to do now. And what he ended up doing was realizing that the amount of his body that went in displaced the amount of water. So he went in, the water went out, and the amount of volume of his body was the amount of volume of water that got kicked out. So if you have an irregularly shaped solid, you still can determine the mass directly by just getting the balance, hitting a tear, and putting a weight on it, and obtaining the mass. But we cannot measure the volume directly. We can't take that little measuring stick, put it in all those little nooks and crannies. Yeah, I can talk. All those nooks and crannies of the crown, we can't, get in there and measure them out. But what we can do, we can take a container that is marked with a measurement. We can put an amount of water in it. Now, when we put the water in there, it has to at least cover the amount of solid material. So we're going to measure the volume with just the water in there. Then we're going to put the crown in there very easily. And we're going to measure the amount of volume that rose, the amount of volume that was displaced. The volume of the solid is simply the volume final minus volume initial. That's going to be the volume of the solid. Did you like my story? Alex, did you like my story?
I did like your story.
Good. I'm happy I'm being able to please you. All right. So we're doing an irregular solid. We fill up a graduated cylinder. Guys, when you're doing this, fill up the graduated cylinder to a certain level. You want to make sure that the amount of liquid is going to cover your solid. All right. Then tip. If you have the graduated cylinder like this cup, you want to tip it. Because if you have a glass graduated cylinder and you just gadunk the solid in there, A, you have a chance of splashing water out, and B, you have a chance of breaking the glass cylinder. But if you tip it and slide it in, nothing really is going to happen. You're gently putting the solid in there. So you measure the amount of volume after the solid's in there, and you subtract the amount that was there beforehand. In this instance, I have 25.3. I subtract 17.8 from that. The volume of the solid was 7.5 milliliters. if I figured out its mass is 6.543, all I got to do to get the density is divide it by 7.5. I get the density. Are we good, guys? We good?
Yes.
All right.
Perfect.
There's another way that you have of doing the graphing. And those of you that submitted your syllabus test and did not upload the picture correctly, now is when you're going to pay for it, because you have to upload the graph and I have to be able to read it. If I can't read it, you don't get any of the 50 points or so that it's due. So be careful about uploading the graph. All right. If you don't upload it, I'll see what I can do about creating a Dropbox, but I need to see the graph. All right. If you want to get the density, a better way to do it, if you just dump the solid into a liquid, all you have is one measurement, right? How many of you trust one measurement? Does anybody trust one? Your life is dependent upon it.
No.
Grazie, grazie. You there, Grazie?
I'm here.
All right, good. Your life is dependent upon getting the density of this bowl correct. Grazie, are you just going to measure it once?
No, probably 5 times or
5
more.
times? Or even better, if you want the density of the glass in a bowl, you'll take the whole bowl. Then you may break off a chunk and take that chunk. Look at another chunk that is there. So you're going to get various samples, and you're going to use various samples to get the density. The glass shouldn't change density. So if you have different amounts, that's going to make your result all the better. Does this make sense? Shake your head, Veronica. I'd like to know that. I'd like to see that people are understanding me. Shake your head, Veronica. There we go. Yes, you're understanding perfectly what we're doing. Fantastic. So what we're going to do when we're doing the density by graphing, we're going to take various samples and we're going to control something. We're either going to control the mass or we are going to control the volume. Okay? So say we're going to do the graph of copper. We're going to control the amount of volume of copper. So when you're graphing, and we're going to get into this very soon, maybe next week or so. When you are graphing something, you have to know what you're controlling. Whatever you're controlling, usually, like 90% of the time, gets put on the x-axis. Now, density is going to be dependent. It's going to be dependent on the volume and the mass. So different volumes are going to weigh differently. So we're controlling the volume. Our volume is going up incrementally. But however much the volume is, the mass is going to differ from that. So we're going to have two different values. We're going to have the mass and we're going to have the volume. And we are going to plot them on a graph. Now, when we plot them on a graph, we're going to have data points. The data points are going to coincide with the volumes that you picked out and how much those volumes measure. Okay? And you're going to go over and you're going to say, okay, it weighed about this much. I'm going to go up that many grams. That's where my first point is. My second point may be right here. So I'm going to put the second point there. My third point may be at 6 cubic centimeters and 40 grams. So I'm going to put it there. My next point may be at 7.5 and maybe at about 65 grams. So I'm going to put it there. So I'm going to have various points on this graph. I'm not going to be able to draw a straight line through them because I have experimental error. But what I am going to be able to do is if I draw the line of best fit so that I average out these points that are above and below the line, what I'm doing is I'm making my density that much more accurate. So what I'm going to do then is I'm going to find a point where it intersects the corner of one of the squares. And I'm going to go over here to 2.5 and up. That happens to intersect the point at 20 grams. That is not a data point. Data points are separate from the points on the line. They can maybe on the line, but I don't want you using data points. So that's going to be one of my values. Then I'm going to go all the way out to 4.75, and that happens to be right at 40 grams. So I have 2 points. Now, how do we get the slope of a straight line? Come on, guys, algebra 1.
Right.
y2 minus y1, x2 minus x1.
Or in other words, delta y divided by delta x. You're going to choose 1 point and you're going to take the y values. You're going to take the y2, the 40, and you're going to subtract 20 from it. Okay? Then you're going to do the same thing with the x values. You're going to have 4.75. From that, you are going to subtract 2.5. Keep in mind the labels that we're dealing with. We're subtracting 40 grams and 20 grams. That's going to give us 20 grams. We're subtracting 4.75 milliliters and 2.5 milliliters. So that's going to give us 2.25 milliliters. I divide the 20 by the 2.25 and I get a slope of 8.89 units. But the units, remember, we haven't canceled out grams. The units on top is going to be grams. Units on the bottom is milliliters. So when we do the slope of the graph of the grams versus volume, we get the density. Questions on that, guys? Some points I want to make. One of which, you are going to get points that are going to approximate a straight line. What you're going to want to do then is you're going to want to draw the best line you can that will average out the points so you get equal numbers above and below the line. Second point, even if one of your data points is on the line, do not use it. Use another point. Don't use data, because guys, if you use data points, why'd you bother doing the graph? The reason you're doing the graph is to average out all these errors. Now, when you're graphing, some rules. You need to use 70% of the graphing surface. You need to determine the range you need to graph. And the way you do that is to subtract your high and low values and divide by the number of boxes you have. Okay? This is my data. Okay? If my X values go, my high value is 45.9 and my low value is 32.5. In order to find the range I need to graph, I need to subtract my high value of 45.9 and my low value of 32.5. Now I got to figure out the scale. That's the range I need to graph, but I need to figure out the scale. The way I do that is I count the number of boxes I have. And I divide the range by the number of boxes, and that will give me my amount per box. If I'm dealing with volume in milliliters, the scale is going to be milliliters per box.
Would that be done in this paper?
Yes.
Okay.
Yes. Okay. So I do this. I do my range and divide it by 20. My ideal measurement per box is 0.67 milliliters per box. Now, guys, is that easy to graph? I mean, you got to sit out there and you got to go out and count. It's not an easy. It'd be better if we had a whole number. So ideally, my box is worth 0.67. It's close to 0.75. And if I choose something like 0.75, I know 2 boxes are going to be 1.5 milliliters, 4 boxes are going to be 3. That's easier to graph. So the other thing you need to realize is when you are doing this, when you're doing this graphing, you are not starting at the origin. You are not starting at 0, 0. You are starting at an X value of 32.5. Okay? We're going to do the same thing with the Y value, only the Y value only has 15 boxes. So again, I'm going to find the range, which is 89.3. I'm going to subtract 62.5 from that. That is my range. And if I have 15 boxes, then my scale is going to be 1.78 grams per box. Now, when you're rounding, you can round up, you can never round down. If you round down, what will happen is you will run out of graphing space. So, to get into, if we decide we're going to round this up to 2 grams per box. Okay. So if my scale is 2 grams per box and I have 15 boxes, I have the capability of graphing 30 grams. Does this make sense, guys? Again, I'm throwing into math here, guys. If my lowest value is 62.5 and I add the range of my graph as 30, I can graph up to 92.5. Does that make sense to you guys?
Will you be posting this slideshow to?
Yes. Yes. Now, if my highest value is 89.3, I've just proven that I can graph up to the 89.3. I can graph as much as 92.5, but I only have to go to 89.3. So if I subtract those two, I need to be able to graph. What I'm not using is going to be 3.2 grams. I divide that by 2 grams per box. And this means I'm not using 1.6 boxes. This means to you that I am not using 70%. Guys, you can use this, or you can just say, Mr. Popovich, that's all well and good, but that's too much math. I don't want to deal with that crap. So I'm going to do it myself, and I'm going to measure it out and see how close it is. I don't care how you do it. Bottom line is 75% of the graph surface needs to be covered. And we are going to get into this a little bit. so that we are gonna get into this a little bit. So we're gonna do it more in depth next week when we get into graphing. And basically, that's all I have to say about the theory behind what we're doing. Any questions, guys? Please, I'm here. So if it's okay with you, I am going to stop this share. And hopefully I'm going to be able to somehow, yay, pull up the lesson. Now, for this one, you are not watching videos. What you are doing is you're going down. This is the home page. This is a course content page. Go all the way down in the course content until you see a module, student data for lab. Click on it. Then you're going to have to go back up again. And you're going to have to download it. All right. So I got to move this. So are we seeing this on the page, guys? Are we seeing the data page?
Yes.
Yes.
All right. So this is where you're going to locate all the information you need to complete the results section. We all clear on that?
Thank you.
All right.
Do you want us to write it out like that, like how you have it? Like volume of water is this, initial volume is this.
All
all of
right.
that.
Who's talking?
Madison.
Madison. Okay, Madison, do you have your laboratory printed out?
No.
Okay, that would be a good idea from now on, okay? If you look, Madison. Okay, Veronica, can you see Veronica?
Yes.
All right, Veronica, could you put the data page? I thought that was it, Veronica. Okay, Madison, if you look here, scan it up, Veronica, scan it up. Move the paper up. You're going to have a place where you can put information. Okay, Madison?
I see it.
Eventually, you're going to have to put that in your notebook anyway.
Okay.
I don't care how it gets in there, but it has to be permanently placed in your notebook.
Okay.
Fair enough?
Fair enough.
All right. So you're going to place all this information on that data page. And you're going to do a calculations page. Now, I'm going to get out of here for right now, go back to course content. And I'm going to go back to the experiment itself, or go back to the I'm going to go back to the lab manual. And again, everybody is still seeing my screen. All right, now I got to move you guys over there. Okay. Procedures. All right, when you're doing this, you're going to have an aluminum bar and a glass sphere. You're going to need to get the mass of it. So basically, if you were doing this lab in person, you literally take the little aluminum bar, put the balance, hit the tare button so that you subtract all the weight on it, put it on there and get the weight. Do the same thing with the glass sphere. Okay? Whenever you're doing a weight from a balance, make sure you record all the digits. All right, next step, you're going to do the volume. They're both regularly shaped objects, but you're going to do the length, height, and width of the aluminum bar. And you're going to measure all three of these, and you're going to use these three measurements to determine the volume of your aluminum bar. To the glass sphere, you're going to do that by Archimedes' principle. You're going to add exactly 15 milliliters of water to it. You're going to softly drop that glass sphere into the water, and you're going to note the new volume, and you're going to determine what the volume of the sphere is by subtracting them. Easy enough. You've got the mass of the objects. You've got the volume. You need to determine the densities. I'm not doing too good with the bar, so I'm going to try the arrows. That may help me. Okay, so we got part C. Now we're on to the density of the water. Okay. All right. The way they do it here may be different from the way that it is entered. I'm going to have to get out of here for a second. So I just want to make sure that I'm telling you right. Boom, 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 boom. Okay. All right. What is happening in the experiment is they are using a burette to deliver the water. They're using a burette because a burette can be read out to the hundredths place. If we were just using a graduated cylinder, then that would only be accurate out to the tenths place. So we're using a burette. And what they're telling you, what they told you to do in the experiment was measure the initial volume, put about 5 milliliters in, stop it off, and measure the final volume. The way you know how much is in the flask is you take the final volume, subtract it from the initial volume. He's done that for you. All he's doing is giving you the volumes. Then you know how much the empty flask weighs. Each time you're adding more amount of water, that's the weight of the total water and the flask. So to get the weight of the water, all you're going to do is subtract each of these numbers from the weight of the Erlenmeyer flask. Are we good with that, guys?
We subtract the total mass of the water and the flash flow, right?
Yes, for each one of these, okay? For each one of these instances, okay? Each one of these is a separate amount of water, okay? So what you're going to do, the total volume added from the first one, you put 5 milliliters in, right?
Mm-hmm.
So you originally weighed the Erlenmeyer flask, you put the 5 milliliters in, and you put the flask back on the balance. Okay? So to get the weight of that 5 milliliters of water, subtract the mass of the water and Erlenmeyer from the weight of the Erlenmeyer. Okay. Then you're going to take that Erlenmeyer flask, put it back under the burette, add another 5 milliliters, stop it off, measure the final volume, subtract it from the original volume, and that gets to be 10.05. you put the volume of the 10 milliliters onto the balance. So the 77.8501 is the weight of the 10 milliliters of water and the Erlenmeyer. Subtract the weight of the Erlenmeyer from it, you get the weight of the 10 milliliters.
Okay.
Are we good with that? We good? All right. That's not what I wanted. Okay, so then what it's going to tell you to do is okay, it's in here. You're going to do all that. You're going to calculate the density using the mass and volume for each trial. He didn't tell you to graph it?
It's further down.
Okay, then you're going to have the total mass and the total volume. You're going to get the densities. Then for the post-lab questions, you're going to need to refer to the table. And you're going to need to do a graph of the volume versus the mass. I know I saw it in here somewhere.
It's in the post-lab questions. It's questions 3 and 4.
Thank you. Thank you so much.
You're welcome.
Okay. So you are going to have to graph it. And it may seem silly, and I could have just said, okay, don't bother. But the problem is if you go into the quiz, if we go into the results section for the quiz, it's going to be there. So rather than get surprised later, all right, guys, you tell me how easy this lab is. All right, you get 10 points for just copying the mass of the bar and the mass of the sphere. From the data table I give you in here, you get 10 points. Woo-wee! We happy about that? Kara, you don't look very happy about it. You don't look happy, Kara. Do you want me to do more? Is that what you're asking me to do?
Oh, sorry,
okay,
I was
guys,
on mute.
Kara wants me to make you do more.
It's my only hopes and dreams. That's what I wanted. That's what I wake up to every day. How can I do it?
All right. So guys, all you got to do is put the mass of both in there. You get 10 points. All right. You got to show the volume calculation for the aluminum bar. This is the one where you do the length, width times height. All right. Then you got to do the volume calculation for the glass sphere. Remember, for the glass sphere, you're doing the displacement. You're doing the Archimedes principle. So for that one, final volume minus initial volume. Show the density calculation. You've got the mass, you've got the volume. You're going to do the same thing for the glass sphere. Again, guys, show the work. If you don't show the work in here, you lose the points. Then you're going to, for trial 2 only, you're going to show how you directly calculate the density of the water from just trial 2. Actually, I don't care, just any one of the trials. It doesn't really matter. Now, because you need to do the graph, you need to upload it here. That's why I was telling you to do the graph. The graph is worth 20 points there. Simple, easy peasy, guys. That's all I have for you. Short and sweet. Out of here in an hour.
Professor, I would like to talk to you in private after everyone's gone.
Okay, no problem.
I want to ask you one question about chemistry that I've been asking myself for a couple of days, and I don't know how to figure it out. I try to look for videos, and I don't know the name of what I'm looking for, so I don't know.
I'll give it my best shot.
Okay. Let me look at the notes.
By the way, guys, everybody else, you're here of your own accord. Class is over. If you want to stay, ask questions. I'm here to answer them as long as you have questions. Go ahead, Veronica.
So remember in the post lab that you told us about the valence of the molecules and stuff? I don't remember how do you get the numbers under? Like, I know you sometimes you cancel like the oxidation number. How do you know them?
Okay, Veronica, I'm sorry. Right now I'm confused. Okay. Can you give me a
this?
Oh, is this the chemical equation?
Yes.
Okay. All right. I'm going to stop share right now and I'm going to share screen. All right. Basically, doesn't matter which one I use because I'm going to go to the very end anyway. All right. Veronica, I believe all they're asking you to do is to balance the equations. Am I correct?
Yes, but I don't remember how do you get the numbers. I know that I remember from high school. I don't remember actually how to do it.
Okay.
You put
so
yeah.
Let's get an equation out here, okay? All right. I have okay, I gotta feel okay. This is kind of what you want, right?
Yes.
All right. Now, we're predicting this. All right. Let me hold on. Veronica, this is going to be a lengthy explanation. If you can hold off. Brian, do you have something?
Yeah.
Do you have something quick?
It was actually, no, it was actually relating to this exactly. It was
okay, that's fine.
How
that's fine. That's perfect. I'm just trying to make sure that you're not here unnecessarily. Mac, were you the one that wanted to talk to me later?
Yes, sir. I'll stay. Don't worry.
No, Mac, I'm sorry, but I have to go through this.
No, I'll stay and watch this. It's okay.
All right.
I'll wait if you don't mind.
Okay, no problem. All right. Now, I know you haven't had this yet, but we kind of alluded to it in our conversation last week. What type of reaction is this? Do you recognize it?
The one that has the two, but I don't remember the double
replacement. Okay.
Double replacement.
All right. Do you remember, Veronica, what happens in a double replacement?
They swap.
They swap. So my cation my cation is going to attack the anion of the other compound. Okay? And my cation from my other compound is going to attach with the anion of the first one. Does this make sense to you?
Yes, I get that part.
All right. Now, what I'm going to tell you to do, put them together first. Okay? Put them together. Take the cation of the first one, put it with the anion of the second one. Just put them together. Then we'll figure out what the subscripts are. Okay? Then you're going to put the cation of the second one with the anion of the first. Do you notice I don't have any subscripts for the ions yet? Do you see that?
Yes.
The 3 on the O in NO3 is part of that. It's part of that ion. It has to have the 3 in it. Okay? So now I'm going to try and figure out what the subscripts have to be for PbCl in order to have a balanced chemical. Because I got to balance the chemicals first before I can balance the chemical reaction. Okay?
Okay.
Now, do you know what the charge on an NO3 is?
No.
Brian?
-1.
-1. Okay. But how many are there of them, Brian?
4.
There are 4 NO3s at -1 to only 1 Pb. So what's the charge on the Pb?
+4.
+4. Did you see that, Veronica?
So they swap.
No, I'm looking. Right now, I'm just looking at this compound. Lead, NO3, taken 4 times. Okay? What Brian said is that NO3 has a -1 charge, but there are 4 of them. So this means there's a total of a -1 times 4. There's a total -4 contributed by the anion. In order for PbNO3 to be balanced, to be neutral, plus charge must equal negative charge. So if the NO3 contributes in total a -4, then that means the lead has to contribute a +4 in order for the compound to be neutral. Does that make sense, Veronica?
Yes.
All right, so the +4 is distributed amongst how many leads? What's the subscript for the lead in that compound?
1.
So that +4 is distributed amongst 1 lead atom. So what's the charge on the lead?
4.
4. Now, when you're doing double replacement reactions, you have to assume that the charge gets carried over. All right? So if lead is a +4, do you know what Cl is, Veronica? What's the charge on Cl?
2.
Nope.
1.
1. Okay. So if lead is a +4, how many Cl's do you need?
1.
If I have 1 Cl, this means I have a +4 from the lead and only a -1 from the Cl. That means I don't have a balanced compound. What I have is something that has a +3 charge on it. Remember, I want to have a neutral molecule. So how many Cl's do I need? If lead is a +4, I need 4 of them. So I get 4 of them by making a subscript. Does that make sense to you, Veronica?
Yes.
All right. Similarly, we're going to look at the aluminum. Okay. You may remember that aluminum is one of the funky ions that always is a +3. But if you didn't, you know that chlorine is a -1 and there are 3 of them. If there are 3 chlorines, each one is a -1, what does the charge on that aluminum have to be?
3.
3. So I'm going to carry it over here. So the aluminum is a +3. we decided that the NO3 is a -1. So how many NO3s do I need?
3.
3. And the way I do that is I have to put parentheses around it. And then outside of the parentheses, I have to put a 3.
Okay.
Is this all making sense, Veronica?
It does. Yeah.
Brian's making sense? All right, now we have to go and balance it. We have all the chemicals are balanced. Now I have to balance the chemical equation, okay? The best way to do that is to have a system. And my system says I balance all cations except for hydrogen. Then I balance all anions except for oxygen. All cations except hydrogen, all anions except oxygen. Okay?
Okay.
Then I balance the hydrogens. Then I balance the oxygens. At that point, I check it and see if everything's okay. Because generally speaking, it usually is. So Veronica, how many leads do I have on the left side?
1.
Right side?
1.
Balanced. Brian, aluminum's on left.
1.
Right?
1.
Balanced. Okay. Now, how many nitrates, Brian, do I have on the left?
3 times 12.
No. I need the 3 oxygens to make up the NO3.
Oh, okay. So 4.
I've got 4. Remember that. If I have a parentheses, everything within that parentheses is the anion family. And you have to carry everything in it to keep it that anion. So I have 4 NO3s on the left. How many do I have on the right?
3.
Fix it.
Then you make...
We balance compounds with subscripts, which is what we did earlier. Now we're balancing reactions. We balance them with coefficients. So if I have a 4 on one side and a 3 on the other, what's the least common denominator between 4 and 3?
12.
12. So how many do we have to multiply 4 by to get 12?
3.
So I'm going to put a 3 in front here. Okay? And how many do we have to multiply 3 by to get
4.
12? Okay? Good enough? All right.
Yeah.
Now, Veronica, how many chlorines do I have on the left?
3.
How many do I have on the right?
4.
So how am I going to balance them?
You're going to add up a 3 in the front and then a 4 in the other one.
Okay, but which one do I have the 4 in?
And AL.
Okay, so I'm going to put 4 there, and I'm going to put 3 there.
Mm-hmm.
Okay, now I'm going to check it. 3 leads, 3 leads, 4 aluminums, 4 aluminums, 3 times 4, 12 nitrates, 4 times 3, 12 nitrates, 4 times 3, 12 chlorines, 3 times 4, 12 chlorines. I am balanced. Now, Veronica, if you were asking how you determine the number of atoms, if that was a question you're asking, what you have to do is you have to take the coefficient that's in front of the compound and multiply it by the subscript. So in the case of lead, the coefficient in front of the whole molecule is 3. I multiply it by the subscript for lead, which is 1. So there are 3 lead atoms.
Mm-hmm.
Okay, now let's look at the nitrogen. The nitrogen has a 1 inside the parentheses. It gets multiplied by the 4 outside the parentheses. So there are 4 nitrogens. That gets multiplied by the 3 coefficient. So there are 12 nitrogen atoms.
Okay.
With the oxygen, again, the subscript inside the parentheses gets multiplied by the subscript outside. So I got 3 times 4, which is 12. That whole thing gets multiplied by the 3 outside. 3 times 12, there are 36 oxygen atoms.
Okay, so you multiply between parentheses first, the 2 of them, and then what you get over there, you multiply with a number outside.
Yes. Let me see. The perfect one. Are you seeing this thing that says counting atoms?
Yes.
Okay. Rule number 1, the symbol will always represent 1 atom of that element. So if you just have the symbol there with no subscript, it's 1. Rule number 2, the subscripts, they're the little numbers to the left and below the symbol. They tell you more than 1 atom in the molecule. So if you have F2, this means 2 fluorine. In the case of the NO3, this meant 3 oxygens there.
Okay.
Rule number 4, if you have a big number in front of the whole compound, everything in the compound gets multiplied by the big number. Coefficients multiply everything in the compound. If the molecule has a coefficient and a subscript, in order to determine the total number of atoms, you multiply the coefficient by the subscript. So if I have 2 S8s, in order to determine how many sulfur atoms, I multiply 2 times 8, I've got 16 sulfur atoms.
Okay.
If a compound has parentheses and a subscript, the subscript multiplies everything within the parentheses. So if I have this compound, Mg3, parentheses, PO3, and parentheses 2, I know because there's a subscript on the magnesium that there are 3 magnesium atoms.
Mm-hmm.
The subscript on the phosphorus is 1. That gets multiplied by the subscript outside the parentheses. 1 times 2, there are 2 phosphorus atoms. For the oxygen, it has a subscript 3 inside the parentheses, a subscript 2 outside the parentheses. So 3 times 2, I have 6 oxygens.
Okay.
And the last rule, if it has parentheses, a subscript, and a coefficient, they all get multiplied by themselves, by each other. So if I have calcium nitrate, if I have 2 calcium nitrates, the 3 subscript for the O gets multiplied by the 2. So 3 times 2 is 6. That gets multiplied by the coefficient. 6 times 2 is 12. All told, I have 12 oxygen atoms. Is this kind of making sense to you now, Veronica?
Yes. It's coming all back together again.
Wonderful. Wonderful.
Thank you.
Okay, guys, I've left Mac waiting for a while. So if you can,
It's all good. I learned something too.
I beg your indulgences because he wants to talk to me privately. Okay? So see you on next Wednesday.
Yeah, bye.
All right.
Thank you.
Thank you.
Okay, Mac.
How are you, sir?
Okay. There's some reason I'm getting a reverberation here.
Of what?
I'm getting an echo.
Oh, it's my laptop. My laptop is messed up.
Okay.
I'm working on fixing it soon.
All right. What can I do for you, Mac?
I made a very dumb mistake, sir.
Okay?
I thought today was the 26th, and I thought all the assignments were due today.
The amazing thing, Mac, is you have a drop.
So each assignment will drop?
Yes.
Okay.
If you forgot to do the pre-lab results and post-lab, those three will drop.
And so pre-lab, post-lab, and results. How about the chemical and physical change in property lab book?
The notebook, you can still hand that in.
All right, I will email it to you as soon as possible, sir.
No problem.
Thank you so
Mac,
much. I
I'm
appreciate
sorry,
it.
but
Oh no, it was my fault. I thought today was the 26th.
And really and
I
truly,
understand.
Mac, what happens is the answers are already published, so I can't do anything about it anyway.
Yeah, I didn't even know it was due today, so I didn't see anything, but I understand. I understand.
What's going to happen?
As long as it's not going to affect me, I'm good.
No, it won't affect you. So what you're going to do, we did the density lab tonight.
Yeah, I have.
That means next Tuesday, the density result and the density post lab are due.
Yes, sir.
As well as the next lab. And that is hydrates. You're going to need to do the pre-lab of the hydrate.
All right, I'll get the notebook notes as soon as possible to you. If not tonight, it'll for sure be tomorrow. Because tonight is at 8:30 almost, so.
Yeah, I understand.
All right, thank you so much, sir. I'll see you next class.
See you next class.
Have a good night.
Night.